I'd like to describe section 13.3 on coloring graphs with many colors. The definition is that a graph is k-colorable if you can use at most k colors to color the vertices such that adjacent vertices receive different colors. In other words, if two vertices are connected by an edge, then they have different colors. An example is that the complete graph on n vertices is n colorable, but not n minus 1 colorable. So you can use n colors, but you can't get away with n minus 1. As an example, take K4, the complete graph on 4 vertices. We can color this graph with 4 colors, blue, red, yellow, and green, and adjacent vertices have different colors. However, 3 colors won't suffice. More generally, for Kn, n colors suffice. Each vertex gets a different color. N minus 1 colors don't suffice. By the pigeonhole principle, if you have n vertices but only n minus 1 colors, 2 vertices are going to have to get the same color, and those vertices will be adjacent. It follows that any graph containing a copy of Kn is also not n minus 1 colorable. If you can't even color Kn, then you can't color this larger graph containing Kn with n minus 1 colors. Now in the last section, we saw a beautiful algorithm for deciding whether a graph is two-colorable or not. Start with a vertex, color it red, all of its neighbors color blue, all of the neighbors of those vertices color red, all of the neighbors of those vertices color blue, etc. You have these expanding neighborhoods that alternate colors, red, blue, red, blue, red, blue. If that coloring works, then the graph is two-colorable, whereas if that coloring doesn't work, then the graph is not two-colorable. Unfortunately, no such algorithm exists for deciding if a graph is three-colorable or four-colorable. Let me try to explain the difficulty that happens. Start with an initial vertex that you color red. Its neighbors, here we've colored blue and green, as is required. But now we have a lot of choices to make. This next vertex could be either red or green. This vertex could be red or green. This vertex here could be red or blue. And this vertex could be red or blue. So the number of choices that you can make at each step explodes. And if the graph gets large, it's going to be too many choices for us to keep track of. That's not a formal proof that this problem, deciding whether a graph is three-colorable, is hard. But it is true that deciding whether a graph is three-colorable is hard. A statement is that in the worst case, if you have n vertices, then deciding whether your graph is three-colorable or not takes time, approximately 2 to the power n over 2. So if you have 100 vertices, deciding whether it's three-colorable or not is going to take time on the order of 2 to the 50th power. That's expensive. 2 to the 50th power is a large number. So in general, deciding whether a graph is three-colorable or four-colorable is quite hard. However, I want to give one theorem, Brookes' theorem, that gives a particular case when you can decide whether a graph is colorable with a certain number of colors or not. Brookes' theorem states, if every vertex in a graph G has degree at most D, then the graph G is D plus 1 colorable. In our example drawn below, we have a graph where every vertex has degree at most 3, and so Brookes' theorem would imply that this graph is four colorable. 4 colors suffice. We're going to prove Brookes' theorem by induction on the number of vertices. If the number of vertices is less than the number of colors, D plus 1, then we can just use a different color for each vertex. And that's our base case. That gets us off started. We're able to color graphs with D plus 1 colors if every vertex has degree at most D and if we have at most D plus 1 vertices. Now for the inductive step, we're looking at graphs of degree at most D, and we'll presume that graphs with n vertices satisfying that property are D plus 1 colorable. We need to show that graphs with n plus 1 vertices, one more, are also D plus 1 colorable. So take some such graph. This graph here has degree at most 3. We'll delete a vertex v to go from a graph with n plus 1 vertices down to a graph with n vertices. By an inductive assumption, this graph is d plus 1 colorable, in this case, 4 colors. And now, we need to prove that the larger graph with n plus 1 vertices is also d plus 1 colorable. So we're going to add back in this vertex v. How do we color this vertex v? Well, v was connected to 3 other vertices. Here it was connected to a vertex colored red, blue, and purple. But we have 4 colors at our disposal. We have this leftover remaining color yellow that we can use to color this vertex v. More generally, this vertex v is connected to d other vertices. However, we have d plus 1 vertices at our disposal. So there's one remaining color not used by any of the neighbors of v that we can use to color v. All right, so that's the argument for Brookes' theorem. You can by induction color your smaller graph with at most d plus 1 colors. And then when you add in a vertex of degree at most d, well, you have one more vertex color than you have neighbors for that vertex. So hence you can complete your prior coloring to a proper coloring on this larger graph with one more vertex. This section continues with a remark that I'd like to give. There's a stronger version of Brookes' theorem, which I won't even describe here, but you can read about it if you're interested. The stronger version of Brookes' theorem is much harder to prove, and so for our purposes, we'll restrict attention to Brookes' theorem. And next class, we'll continue with a description of some examples of graphs. Here's a graph that will show is not 3 colorable, and here's another graph that will also show is not 3 colorable. Thanks.